Okay, I think we can begin. We have about under 30 people. All right. So welcome to week 10 of AI504. So this week we're going to talk about recurrent neural network RNN. So last week was well, we talked about word to vec and subword encoding and contextualized embedding. So that's kind of like a primer or introduction to the world of NLP. And now we're going to talk about probably one of the most famous architectures, popular architectures in NLP, which, I mean, it used to be the most widely used architecture, probably up until like 2018. And then after 2018, Transformer took over. So RNN is not as widely used as before, but still it has its place. So and, a lot of ideas came from this RNN. So it's worth taking note and paying attention. Right, I'm going to mute everybody. Right. So yeah, we're going to talk about the very basics of RNN, which is just vanilla RNN, and then talk about bidirectional RNN, GRE and LSTM, which have gates that kind of helps RNN remember important information and forget not so important information. So that's the architecture of RNN. And then we're going to talk about sequence to sequence, how to do basically RNN was first, I mean, RNN was proposed like way back in like 90s or 80s, like really, really long time ago. But the idea of sequence to sequence came about in 2014. It was proposed to do a translation, English-French translation. So a lot of modern architectures came from machine translation researchers, like transformers, the attentions, all of that, So we're going to talk about sequence to sequence and then end with attention. So with the attention in mind, we can move on to next week's material, which would be transformer. Right, so recurrent neural network. So the core idea of your recurrent neural network is handling variable length sequence. So if you think about image to label, as we talked about, what machine learning basically is that we want to learn a function that maps samples from domain X domain to the whole domain Y. So we want to learn a function. So if it's image to label function, then there's a bunch of images like, cats and dogs and people and whatnot. And then there's finite number of classes. So this could be a dog, cat, human, car, whatever. And then we want to classify or map an element in this set to an element in this Y set. And if you think about image to label versus sequence to label, so there's a fundamental difference between image to label and sequence to label, because in image to label situation here, we usually have a fixed sized input, So image, we usually deal with 128 by 128 RGB channel. So that would be 128 by 128, 128 by 128 by 3. Or if you think about MNIST, it's just simply 28 by 28 by 1 because it's black and white. Usually once we decide which problem we're going to solve, if it's MNIST classification or it's ImageNet classification, Cypher 10 classification, if we decide on the problem, then the input doesn't change. The size of the input doesn't change. But if you think about sentence to label, for example, if you want to do a like sentiments classification, we have a sentence. I am happy to see you, whatever. And then we want to classify whether this is a positive sentence or a negative sentence. The set would be all English sentences, right? All English text. And then the Y domain would be, the codomain would be, Y would be positive or negative. It's just, two elements, set with two elements. So any element in this X domain should be mapped to one of these, one of this. So the problem is set. We want to solve a sentiment classification where the domain is all English sentence, and then the problem arises where English sentences don't have a fixed length, It could be as long, it could be infinitely long, You can just keep adding words to a sentence to make it as long as you want, or you can make it as short as you want as well. So the lengths of the sentence or the size of the input can change. It varies. So that is the fundamental difference between image to label and the sentence label. So if it's image to label, we can just simply use, even if people use CNN, but we can even use MLP, we can use a simple feed-forward neural network to do a very simple image to label classification, such as MNIST classification. MNIST, you can just do it with, multi-layer perceptron. With sentence, you can't do that because, your input changes, your input size changes all the time. Yeah, so yeah, size fixed, varies by sample. So that's the fundamental difference. So classical way to handle variable length sentence or documents. So what did people used to do? What did people used to do when they wanted to handle variable length sequences, such as sentences or documents? So for example, we talked about this in the previous week with term frequency type of thing. Term document frequency matrix. So for example, if you're given a sentence, I gave the ball to John, who gave it to Mary, then how many words does it have? It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 words. So it could be 11 words, it could be 10 words, it could be 20 words, doesn't really matter. So the way that you can handle variable length sentences or documents is to, as shown before, count the number of times each unique word or each unique vocabulary occurs in this sentence. So it's like I 1 times, gave 2 times, the 1 times, all yada yada yada. So if you think about the number of unique words in the English dictionary, that is your entire space. Your dictionary doesn't change. So for example, if your English dictionary consists of 50,000 words, then all your sentences and documents and whatever text can always be represented as a 50,000 dimensional vector, where each element corresponds to a single word, and the element's value would be the number of times that word occurs in the sentence. So if you can think about 50,000 dimensional vector, where everything is almost everything is 0, and then sometimes it's like here it's gave, and then actually ball should be here in the front. John should be here somewhere. John should be here somewhere. Mary comes after. Basically something like this, So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 words in the sentence, and out of 50,000 words in the entire English dictionary, only 9 elements, 9 components would be non-zero, and everything else would be 0. So that's one way to do it. Yeah, just like this. So you have all vocab, which could be 50,000. And then you can just count the number of times each word occurs in the sentence, and then all your sentence, all your text, all your documents, all your paragraphs, whatever, is always 50,000 dimensional vector. But then we talked about how it's not a very good idea. If you think about the way we talked about the word embedding and how like a cat 0, 0, 0, 1, 0, 0, whatever. Cat could be represented in 2 ways. It's either a one-hot vector or a continuous valued vector, which we call them distributed representation. And obviously the latter was better, because slightly perturbing the values of the cat vector, distributed representation vector, doesn't change the semantics that much. So we talked about all the advantage and disadvantage of word embeddings and the continuous representation. So clearly, this kind of discrete count-based representation is not the most ideal representation. Right. So here's a very good example of that. I gave the ball to John, who gave it to Mary. That's one sentence. Another sentence is I gave the ball to Mary, who gave it to John. So clearly these 2 sentences represent different meaning. The first one is that John first receives the ball, and then John gives the ball to Mary. But in the second sentence, Mary receives the ball, and then she gives it to John. So it's clearly 2 different sentences. But if you count the number if you represent it in the counting vector style, then you would get the exact same vector, exact same 50,000 dimensional vector. So different meaning, same representation, which means that this way of representation, this method of representing text or sentences is not the most optimal way to do it, because clearly there are two different sentences. So it means that two different sentences. There's sentence one and sentence one, sentence two. And so this is the old English sentence. This is representation space, representation space. They are mapped to the exact same place. Not a good idea, right? So we need something better. So classical NLP all depends on this kind of stuff, this, counting vector, one-hot vector, this all, all these are like all these syntax, semantic, discourse, all these classical NLP concepts have like very different layers of handling sentences or words or documents or paragraphs, basically text. You start with, there's different levels of concept, like there's syntactic level, there's semantic level, there's discourse level, pragmatic level. You start with, and you have a bunch of tools to analyze in different levels. In order to analyze syntactic level, you need to first do a part of speech tagging and parsing. In order to do semantic level analysis, you need to do named entity recognition, semantic role labeling. Further, in order to do discourse, you need some other tools. In order to do pragmatic analysis, you need another tool. There's always different tools for doing different levels of analysis, and all these are made obsolete by deep learning. Well, I mean, at least not these concepts or these tools are not used as much as before, because it ultimately in NLP, what people want to do is, develop a machine that can understand and speak human language. Basically a perfect chatbot. Probably I would say that's the ultimate goal of NLP. And in order to do like a chatting, in order to do it like a dialogue, like open domain dialogue, like or task oriented dialogue, in the pre deep learning era, people used to do all these things. In order to understand a human language, they had to go for all these and then analyze the spoken sentence in various levels, and then based on that, a chatbot or a machine would generate or respond with the text. So in order to understand, they had to do this. But in these days, what we do is we simply just put the human language into RNN or transformer, like a gigantic model, and then let it figure out. We don't do any of these. We don't do this. We don't do this. We don't do any of this. We just dump bunch of text without doing any of this analysis, and then just let it figure out with transformers or whatever, and then just generate with sequence to sequence architecture, and then there you have your chatbot, which performs way better than before, way better than pre-deep learning era chatbots. So that is why we might be able to say that all these are made obsolete and no longer used anymore. But or are they? They have their places, but they're not as popular as before. All right, so the thing that all started, the thing that made these all kind of obsolete is that sparked the whole movement is RNN in 2013, 2014. So what is an RNN? RNN is a model that can handle variable length input. So it's a perfect architecture for handling sentences or text, or even time series or whatever. It's basically used for handling sequences, but especially a good fit for NLP. So RNN represent variable length input, or to better put it, we encode variable length input. Encoding means that accepting input and then representing in the embedding in a lower dimensional latent semantic space, representation space. And its update equation is super simple. This is the only equation you need to know. So H is hidden layer, and T, so let me just blow it up a little bit. So H is your hidden layer, and T is your time step. So if you have a word like I am a boy, then this is your first word. So I'm going to put T equals 0. This is T equals 1. This is T equals 2. This is T equals 3. And then actually, usually we use the termination symbol period somewhere. So there's like end of sentence, T equals 4. So T is the time step index, and H is the hidden layer. X is your input. So XT is your input at the Tth time step. H is your hidden layer, or you can call it a memory, because RNN basically memorizes or remembers all the inputs so far. So your current input, your current memory, your current hidden layer is updated by your current input and your previous hidden layer and the bias, and that's it. So it's a very simple concept. You put your input, and then you linearly transform it, and then you add your previous hidden layer or previous memory, linearly transform it, so that becomes your another component, and then you add those two plus the bias, and then you have your nonlinear activation function. Usually it's 10H. So that's it. And then you keep doing this for H equals 0, H equals 1, H equals 2, H equals 3. Keep doing this each time step. And obviously for H0, which is the very first hidden layer, well, actually here, sorry. So here the time step starts with 1, so I should have put 1 here instead. So it's T equals 1, T equals 2, 3, 4, 5. So H0 is the initial memory. So initial memory is usually randomly initialized, or it's filled with 0. So it's kind of like your choice, your preference. And then starting with your first input, which is I am a boy somewhere, end of sentence. So H0 filled with 0, and then H1 is depending on X1 here, X1, and then it also depends on the previous hidden layer, which is H0, and then you update it, and then you do the same thing again. So basically you're just running a for loop until the end of the input, until the end of the sentence, and that's it. Right, so basically, there's only two learnable parameters. You see that there's only two learnable, because all the others are actually fixed. Oh, sorry, actually 3 learnable parameters. One is W, the other is U, and the other is B, the bias. So W, U, and B. So you're recycling, or you're reusing 3 parameters throughout the entire time, throughout the entire sentence. You don't use different W's and different U's for each input. You don't do that. You use the same W, same U, same B for the entire input. So that's why it can handle variable length input. If you used different parameters for each input, then you can't handle variable length input, right? So U is for transforming your previous memory into the current memory, and W is responsible for transforming your XT, your current input, to the current hidden memory, current hidden layer. So that's it. And I think we're kind of like forgetting about the bias here. So if you think about how similar it is to the feed-forward neural network, you can just simply rotate it. So you have a horizontal representation of RNN, but if you just rotate it 90 degrees, then you can see that it's kind of like MLP. It's just that MLP doesn't have this. If you just lose this side information, then it's just simply you're just propagating your hidden layer from one layer to the other. It's just that in RNN, you also have the side information being new information, new input being fed into the model every single time. So you can imagine how the backprop would work, because in the original feed-forward neural network, your backprop depends on your loss function, which is y prime y. Actually, y hat would be better. Your loss function y. So you start with your loss function, then you backpropagate your error signal to previous hidden layer, like this, right? Like this. But here, because you have another input, another channel where you can propagate where you can backpropagate your error, which is the input channel. So your error signal also goes to here, and then here, come back here, and here. So it's the backpropagation mechanism kind of is complexified, but the fundamental theory is all the same. It's just exactly like feed-forward neural network. It's just that you have side information or new input at each time step, and then you're reusing the same parameters all over and over again. All right, so where do you use RNN for? So RNN is used for basically all sequence handling applications. So sequence level classification regression, which is sentiment classification, topic classification. If you want to classify a news article into different topics like sports, politics, science, society, celebrity, you can use RNN. Or sentiment classification, I just talked about it. Classification and regression. Well, actually, I do have a. Oh, let's see. Okay, I think the different application form, the different architectures for different applications will come later. There's different ways to use RNN. Sequence level classification or regression means that you put all your sequence into the model, and then you use the only one file. Yeah, you perform the classification only once for the entire sentence. Classification at each time step means that you do classification for each input, each word, for example, like language modeling or part of speech tagging, like what part of speech. 그러니까 이제 형태소죠, part of speech가. 이제 지금 들어온 단어가 이제 동사냐, 명사냐, 뭐 형용사냐를 맞추는 거는 매 단어마다 맞춰야 되잖아요. 이제 그거는 이 문장이 긍정적이냐 아니면 부정적이냐랑 또 다른 문제인 거죠. So it's a different task than this one. And then the last one is sequence to sequence, which is translation or chatbot or question answering, because your input sequence and your output sequence can be of different length. So in that case, you need a sequence to sequence or encoder decoder architecture. So I'm going to show you the depiction of all these three scenarios later. So sequence level classification. So sentiment classification. So we're back to the original application. Is the given sentence positive or negative sentimentally? So is it a positive emotion or negative emotion? And if you read the sentence, this movie is as impressive as a preschool Christmas play. It on the surface or in a word level, this sentence seems like a positive sentence because there are a lot of kind of like positive words like impressive. 유치원, preschool, Christmas, play, like these all kind of relate to positive emotion. But if you read the entire sentence, then it means that it's being sarcastic. It means that the movie was not as impressive it was not impressive basically. If it's like 그러니까 이제 유치원 애들이 하는 연극만큼이나 이제 감동적이었다는 건 감동적이지 않다는 거니까 이제 굉장히 비판적인 말인 거죠. So that's why this kind of like shows why it's why NLP is not as easy as you think, because you have to read the entire sentence and then you need to have common sense to understand what this really means. So a lot of basically very it's more like abstract level thinking compared to image classification where you just have pixel level information, which is just photon information, and then you need to classify whether it's a dog or a cat. Compared to that, in order to properly understand this sentence, you need to have a lot of knowledge basically. So how to do this? So with RNN, we're gonna do binary classification. Basically, is a sentence positive or negative? So as I said, you can use in order to represent a word, you always have to at least start with a one hot vector. So you can eventually use word embedding, but in every single time, if you have nothing, if you're starting from scratch, then you need to start with a word index or like a basically one hot embedding. This is the way to represent a single word. So we start with this, and then you have, for example, 50,000 dimensional vector, the entire. Actually, here, okay, so here the example is that a vector with 1 million. So it means that there's like 1 million words, 1 million like unique terms in the English dictionary, which is clearly not true. But let's just stick to the example. So 1 million size vector, and then only one element is 1, and all the other is 0. So it's one hot vector. So this is how you represent a single word or single term in English. So this is the first word. So the fourth place is the place for the word this, and then you put this, you treat this as an x1. This is an x1, and then you put this into your word into your RNN, which is, well, here it's actually hidden. So there's plus U, H0 plus B. It's all hidden. Bias is omitted. H0, we said that H0 is usually initialized with just 0 vector. So this is also gone. So that is why we just simply say this. So you put your 1-hot vector, and then your WI would be the dimension. So you have to, another hyperparameter you need to set is the size of your hidden layer. So size of the hidden layer should probably, correlate with the complexity of your task. So since this is just binary classification, maybe we can just set it to 128. So 128. So your W should be what? It should be a matrix that looks like this. It's a 128 by 1 million. And then you do an inner product between your weight W vector, W matrix, with your one hot X vector, X1. And then you get what? You get a 128 dimensional output. And then you push through, you put it through a nonlinear activation function, and then you get your H1. So that's your first time step. The second time step, you do the same thing. You represent your word movie, as a 1-hot vector, and then you do the same thing. But here, W actually saw. Oh, okay. So instead, here we're no longer using U and W. We're using WH to represent U and WI to represent W. So H for H, I for X. So here we have H1, which is relevant. So H1 is the memory for what word was given in the first time step. So you need to keep that around, and then you linearly transform it, add that with your input at the second time step, and then you add that, and then you get you put it through a nonlinear activation function, and then you get your H2. So you can imagine WH being what? It should be a square matrix. It should be 128 by 128. Because you want your H1 is 128 dimensional vector, and then you want your output to be 128 dimensional vector. So it's got to be, WH has got to be a square matrix. So you get your H2. H2 is suppose that ideally H2 should remember what was given in the second time step as well as what was given in the first time step, because it is your H2 is the summation of your first memory and your current input. So H2 remembers that I just received movie, and then in the previous time step I received this. You do this process over and over again. You do the for loop until you reach at the end of the sentence, which is play. So we're omitting the EOS. So you have the play as your last time step, and then your H10 theoretically should remember what has happened so far. So a play was given in the current time step. Before it was Christmas, before it was preschool, before it was A, all the way to the first time step, which is this. So H10 should be a representation of the entire sentence. So H10 is a sentence representation. So it remembers the entire sentence. So you can use H10 to do like classification or regression or whatever. So here, what we want to do is we want to use H10 to do a binary classification, which is it positive or is it negative? Is a given sentence positive or negative? So H10, so before, if you think about it, before what we used to do is that we had a 50,000 dimensional vector, and then somewhere is like impressive, somewhere it's movie, somewhere it's like preschool, and then you had a corresponding number, like it's how many times? It's once, like a lot of zeros in the neighborhood, a lot of zeros. And then using this counting vector, we would do like classification using support vector machine or random forest or logistic regression, whatever. So this counting vector is the sentence representation. But here now this continuous value, the H10, which is kind of uninterpretable because it consists of like a lot of unintelligible numbers, like minus negative 1.5, 2.6. 0.3, negative 5.4, something like that. Some numbers that just, some numbers basically that is determined by the WH and WI and the bias B. So, but it is way more compact because this used to be 50,000 dimensional vector, but now this is 128 dimensional vector. So we have a way more compact representation of our sentence. And then using the sentence, we do a logistic regression. We have logistic regression weight, and then sigmoid function, a sigmoid activation function, and then you get y, which is whose range is between 0 and 1, right? So basically that's it. So all the learnable parameters, the parameters that you need to update in order to perform binary classification accurately is what? Is one here in the logistic layer, in the prediction layer, WO, and then WI, WH, and the omitted B bias. So you have total 4 parameters that you need to train with backpropagation in order to, perform this binary classification accurately. So you do the same optimization step. You have your mini batch of sentences with corresponding labels, positive and negative, and then you put it through, do a forward propagation, and then you do a cross entropy loss, and then you backpropagate it, backpropagate based on the cross entropy loss. You update your WO, WH, WI, B, and then you do this for the next batch, next mini batch, next mini batch, until you're satisfied. All right, so far, any question with RNN? In some sense, RNN is actually simpler, more simpler than feed-forward network, because you're reusing the same weights over and over again for different layers. Right, so no question. So another application for RNN is language modeling, which is actually still a very, very relevant concept. And language modeling has been around, I don't know, like 30 years or 40 years. Like it has been studied for a very, very long time. And language modeling is basically you want to model language, and that's it. So language modeling is exactly what it says. But these days, people use language modeling to do what? To do, like, if you are familiar with like GPT or Bloom or GPT-J or GPT-Neo, whatever, like all those language models, we call them language models, but in reality, they're used for generating sentences, right? Like writing codes or writing poems, writing news articles, like doing chats with human users. Like basically all these models are used for that purpose. But in a more like academic sense, language modeling is exactly what it says. You want to model language or model any given text. So any given text, you want to quantify how likely the given text is. So you have a entire all English text. So there's like I go, very, very simple sentence text like this: I go, I play, or I am a boy, to very, very complex sentences like like Wall Street Journal news article sentences, like which is like 20 words long or 30 words long. So all infinite number of elements. So this is an infinite set, basically, all English text. And what you want to do, and what language modeling wants to do, is they want to quantify, they want to calculate how likely a given sentence or given text is among all English sentence. If you just choose one element out of this set, and then you want to ask what is the probability of this sentence X out of all the English, which would be very infinitesimally small, because your set is infinitely, as it could. It's not sure if it's truly infinite, but it is almost as good as infinite, right? So out of the entire infinite set, what is the probability of seeing this particular sentence, like this sentence? This movie is as impressive as a preschool Christmas play. How likely is this sentence? What is the probability of this sentence? Which should be super small. So that is the essence of language modeling. And if you can break it down into this, factorize into this form here. So because a joint modeling, like joint probability of the sentence, would be extremely difficult to quantify. So you break it down into a factorized form like this, like P this, probability of this, and then probability of movie given this, probability of is given this in movie, probability of play, all the way to the last one, which is probability of play given this movie, Christmas play, just all words that are previous to the given current one. So this is basically it. So if we can, so this is, everybody knows. Like, I hope everybody knows that this is the same as this. So factorized form is exactly the same as this. So if you can theoretically model this probability, then you can calculate any text's probability, the likelihood or probability of any text, because simply you can just factorize into this form, and then you can just plug here. Well, actually, you need to, the plug needs to go the other way around. You can just plug this model here, 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 and also here. But this is kind of like special case because this doesn't have a previous form. So if you can model this with variable size, this should be a variable size, variable length, right? Variable length. If you have some model like this, then you can factorize any text and then calculate the probability of the text. Basically, that's what language modeling is. Right. So traditionally, people used to do like unigram or bigram or trigram, this kind of stuff. If you're familiar with this, good for you. So unigram, bigram, trigram, it means that unigram means that you only look at one word at a time. Bigram means you consider 2 words at a time. Trigram means you consider 3 words at a time. So there should be like 4 gram, 5 gram, 6 grams. Basically, you call them n-grams. So classical approach for doing language modeling is that you can't classically, before the advent of RNN, which can handle variable length input, people just used a fixed length input for this fixed length window, basically like history. Like this is your W10, this is all your history, right? So people used to do like a fixed length history for language modeling, which if you do it with bigram approach, then it's basically this. You only look at one previous word, and then you just assume that looking at only the previous word is enough. It's kind of like a Markov assumption. In order to quantify the probability of your current word, you only need to look at your previous word, and that's it. Even though that's not true, it's probably not. It's never true. Usually, in sentences, the dependency goes way back. For example, like impressive. This will be impressive. Like for example, like impressive doesn't only depend on the previous word. It depends on is. It depends on movie. It depends on, well, it doesn't depend on this. But anyway, like it has dependency between like is and movie. So it's like two words back and 3 words back. So this very simple assumption is not really realistic. But people used to do it because they didn't know how to handle variable length history. If you do it with trigram, you do it a little better with 2 previous words. Right? So in order to calculate the probability of WT, you need to look at previous word and the word before that, and that's it. So in order to do this, you need to prepare all these different combinations. Basically, in order to do bigram, you need for example, if your English dictionary consists of 50,000 words, then you need a 50,000 by 50,000 by 50,000 matrix. And your first is, what is PA of A? And your last one is, what is PZZZ given ZZZ? And then anywhere here would be like, what is the probability of, what would it be? Probability of, like, yeah, right here, like movie given this. So you need to come, you're looking at all the English sentence, like, like Wikipedia or news articles or wherever, or Twitter. You have a bunch of text, and then you calculate what's the probability of this, basically all the elements in your matrix. You calculate the probability or conditional probability. It's a conditional probability, right? So calculate the conditional probability, and then you break down your sentence into bigrams. This, movie, this, is movie, as is, impressive as impressive, all as, preschool like this. Like, but you break down your sentence into bigram manner, and then you plug your corresponding elements from your matrix into each element, each factor, and then you multiply the values, and then there you have your probability. If you want to do a trigram, you can't do it with your matrix. It needs to be on a tensor now, because you have two more. You need to look at one more word. So there's your previous word, WT minus 1. There's your WT minus 2 on this axis, and then you have WT here. You need to fill your cube looking at all English corpus on the internet, which would be very, very time consuming. So that is why these n-gram approaches are not very scalable. If you want to blow it up to like 4 grams or 5 grams, it becomes hypercubes and hypercubes. It's not really scalable. So theoretically, with RNN, we don't need to worry about that, because we can model the full history, because RNN can be used to model or encode the entire history, because it can handle variable length input. So that is where RNN comes in with to perform like a language modeling. So yeah, exactly like this. This movie is as impressive as a preschool Christmas play. And what you do is you try to predict the next word. So because what we want to do is we want to predict movie this is here. It is so let me just write it in a small. So here this is a special case, because we have no history in the first word. So this is a special case. But starting with movie, what we want to do is, what is the probability of movie given this, right? Given this. And here, in order to do that, what we do is you input this into the RNN, and then you try to predict the next word. That is the probability of movie given this. Then the next time, what we do is, what is the probability of is given movie? Oh, actually, it should be this movie. Make it more readable. What is the probability of is given this history, this movie? And here, this is what we're exactly doing. Given this n movie, so H2 should be remembering this n movie, right? So given this H2, the history, what is the probability of is? So this is exactly doing that. This predicting is exactly this. And you do this for the entire sentence. What is the probability of play given the entire history? What is the probability of EOS? What is given the entire history? That is it. So that is, you train your model to do this kind of prediction for every time step. Every time step, every word, you try to predict the next word. This here, you try to predict the next word. Try to predict the next word. Try to predict the next word. You do this for the entire sentence, and then you backpropagate with the proper cross entropy, because if you think about how many words there are, we assume that there are 50,000 words, then this actually is a 50,000 way softmax probability. So there's A to all the way to ZZZ. There would be like boy, there should be a cat, somewhere in along the 50,000 mentioned, there's play, which is the actual answer. We want this logit to be the highest in this time step. So that is how you backpropagate. So you do a softmax classification for every time step. And if you train your model properly, then your model can properly calculate the probability of a given sentence. But more than that, what you can do with this trained model is you can sample, given this, you can sample what is the most likely word that comes next? Movie. Then given you put this movie into your next input, so given this and movie, what is the most likely word that comes after this movie is. So you put this, and then you do this over and over again. You do an autoregressive sampling. Autoregressive meaning you use your prediction as your next step input, and then you predict, and then you get your prediction outcome. You use that outcome as your next step input. So that's autoregressive sampling, right? So you do this. You predict. You put it in your next input. You predict. You use your prediction into next type input. You do this over and over again. So you have your input. You predict your next step, and then you put that in your input. So far and so forth until you reach the last symbol, end of sentence symbol. So basically, if you have a well-trained language model, you can generate new sentences by doing an autoregressive sampling, and that is how GPT can generate very, very realistic sentences or text, or even Python codes or like SQL codes, like any codes. Hopefully, everybody can understand what language modeling is. So if you can calculate this probability very, very accurately, then you can use it to calculate the probability of a sentence. And more than that, you can use this probability to sample new sentences. Right. So yeah, exactly here. So there's a softmax layer here because you're using your H1 to predict the next word, and the WW here, WW should be what? It should be 128 by 50,000. 128 being the dimension of your hidden layer H1, and then you have your prediction, and then you use your prediction to do a back propagation using cross entropy, and you do this for every time step. And then what you are doing is you're training, or you are updating your WW, and then there's somewhere here W H and WI, and then there's bias. So you're updating 4 parameters. Right. So there's 10 loss terms for a single sentence. Right. So moving on to so that's the language model. Moving on to bidirectional RNN. Bidirectional RNN is basically you're using 2 RNNs to go forward and backward at the same time. So if you remember the sentiment classification, we put this first and then movie after, and all the way to the last word, which is play, which is natural. You start with first word and then you end with the last word. But if your sentence becomes longer, if your sequence becomes longer, then RNN tends to forget the input that the word that you input in the very, very long time ago. Like, you know, if your sentence is like 50 words long, then the first word or second word happened so long time ago, your H50 or your H49 would probably forget H1 or H2. So in order to cope with that, people used to do binary. People came up with this bidirectional RNN idea, which is you put last word first, and then you move backwards in time, like this. You put play first, and then Christmas, and then all the way to the movie and this. So in this way, your S is your hidden layer. Your S doesn't forget. At least at least your S clearly remembers what happened in the first part of the sentence. It might forget what happened in the last part of the sentence, but then H remembers that. So it's kind of like complementary. H remembers the last part clearly, and then the S remembers the first part more vividly, so they can complement each other. So in that concept, that's why you use binary. That's why you use a bidirectional RNN. Oh, actually, there was some question. I just missed that. Sorry. So question from Min almost 20 minutes ago. Why are we sharing weight over the model instead of different weights? So very good question. If we used different weights for each layer or each time step, we use W1 here and then W2 here, W3 here, then you can't put longer sentences than the sentences that you use in the training samples. Do you understand? 승민이 혹시 답이 되셨나요? 그러니까 이제 다른 매 타임 스텝마다 다른 웨이트를 사용하면은, 예를 들어서 우리가 학습 때는 사용했던 문장의 최장 길이가 20단어였어요. 그래서 이제 W1부터 W20까지 사용을 해요. 근데 우리가 테스트 때 25단어짜리 센텐스를 넣고 싶으면은, 그럼 이제 W21이나 W22가 없잖아요. 우리는 준비된 게, 학습된 게 없잖아요. 그러니까 이제 베리어블 랭스를 사용할 수가 없단 말이에요. 그렇기 때문에 똑같은 WH랑 똑같은 WI를 재사용해야지 아무 랭스의 센텐스를 이제 인코딩할 수 있다는 겁니다. 네, 답이 되셨을 것 같은데. 그렇고요. 그다음 이제 혜현님, 매 싱글 타임마다 웨이트를 사용한다고 하셨는데, 학습하면서 파라미터 WXD가 업데이트되면 앞에 것도 싹 다 같이 바뀌게 되는 개념인가요? 그러니까 그 업데이트를 하면은 사실상 이렇게 되면 이제 아까 이렇게 생겼었잖아요. 이렇게 H가 뭐 3, H2, H1, H0 있고, 여기서 이제 X1, X2, X3 있고, 이렇게 가고, 요런 개념이었는데, 이제 여기에 이제 뭐 로스 펑션이 있었다 그러면은 백프랍이 되면은 지금 이게 WI, WH, WI, WH, WI, WH 이런 식으로 이제 구성이 될 텐데, 백프랍을 하면은 얘가 그러니까 WI는 3번 업데이트 되는 거. 여기서 한 번, 여기서 한 번, 여기서 한 번 업데이트 되는 거고, WH는 1번, 2번, 3번, 얘도 3번 업데이트 되는 거고, 그렇게 업데이트 되는 거입니다. 그러니까 앞에 것도 다 같이 싹 바뀌게 된다는 게 맞는 말인지 모르겠는데, 어쨌든 파라미터가 바뀐다는, 파라미터가 총 3번 업데이트 되는 거, 3번 업데이트 되는 거. 각각. WI가 3번, WH가 3번. 네네. 좋습니다. Right. So that's bidirectional RNN. So you have forward RNN, you have backward RNN. So you have H10 and S1, and then you want to use both at the same time, right? Because they are complementary to each other. So you just simply concatenate H10, S1, you concatenate horizontally, and then you use it for like logistic regression or softmax classification. So that's the basic concept of bidirectional RNN. Right, so limitation. So what's the, I mean, so far RNN seems like a magic tool that can handle any variable length input. And then you can do a lot of different interesting stuff, such as, sentence classification or language modeling or sequence, like all that kind of stuff. But the problem is there are certain limitations, which are vanishing gradient. So vanishing gradient, we talked about, I'm not sure if we talked about vanishing gradient in the feed-forward neural, when we were talking about feed-forward neural network. So in feed-forward neural network, if you use too many layers, like 100 layers or 1,000 layers, then your backpropagation doesn't work very well. Because backpropagation is basically, if you think about backpropagation, in the, like, I think we talked about it in the third lecture, where you have FW, X, W, FW, like this, FW, like if you remember this nested architecture of a multi-layer perceptron, like there's F and different, well, in this multi-layer perceptron, the W's would be different. There's W1, W2, W3, W4, W5. So, and then you have your feed-forward neural networks in between. So actually, let me just write it a bit more clearly. So your W1X plus B1 F, and then you have W2 plus B2 F2. Suppose that you use different nonlinear activation functions all the time. And then you have W3 plus B3 F3, so on and so forth, right? If you remember this notation. And when you want to do back propagation, there's a bunch of W matrix multiplications involved in the back propagation, all the way down to the first layer. If you start with the first, so in the first layer, there's no matrix multiplication actually. So you just have a simple loss function, and then you use loss function you differentiate the loss function with respect to the last W, and then you update the W, and that's it. But anything below that, it always involves basically it involves a Jacobian matrix. And then if you do a multi-step backpropagation, your Jacobian matrix will either vanish, which means that it'll go a lot of values in your matrix would be 0, or it would explode. It would explode, which means that some values in your matrix would go to like almost as high as infinite, like positive infinity or negative infinity. So that kind of unstabilizes your backpropagation process. So that is why your error signal usually doesn't reach all the way to the bottom with a proper ranged value, because either your values go to 0 or your values explode. So in order to cope with that, people came up with ReLUs and batch norms and residual connections and all that. So with the advent of residual connections, so ResNet, so no longer people have to worry about this kind of stuff. But back in the day, this vanishing gradient and all this was a big problem. So the same problem exists if you use too many layers in feed-forward network. There's a problem, which is vanishing gradient and exploding gradient. Same manner with RNN. If you use too many input, if you use too long sequence as an input, like 500 word length sentence or 1,000 word length, 1,000 word length sequence, if you use that long sequence, then your gradient will not actually backpropagate properly. So same manner, same problem exists. So vanishing gradient still exists. Long sequence means long backpropagation chain doesn't work. And another thing is input from a distant path is forgotten. Exactly as I said here. If you use like 50 words or 100 words, then your H100 would probably not remember H1 or H2 very well. So that also is forgotten. For example, but the problem is that you sometimes need to really remember what happened in the very, very past. For example, in order to solve a problem like this, like you have a very long sentence, and then you want to fill this last word, you actually need to remember what happened in the in the past. Like Jane walked into the room, John walked in too. It was late in the day. Jane said hi to who? To John. So you need to remember what happened in the past. You can't just remember very recent past like RNN does. So there's another problem. So how do we remember? How do we cope with this problem? How do we resolve this two limitations? So some old tricks use initializing weight matrices to identity matrices or using values. Like there's some neat tricks that could work well, but doesn't fundamentally solve this problem. So what people did, and exploding gradients can be resolved by gradient clipping. You just you clip the value, the length, the size of, you clip the norm of the gradient to a certain size so that your gradient doesn't become too long. I mean too large. But all these are kind of like a remedy. So that's where LSTM and GRU comes in order to cope with this kind of like vanishing gradient problem and forgetting your distant past. Then all these limitations can be remedied by GRU and LSTM. So GRU is a variant of RNN, but uses more complex hidden unit computation in the recurrence. So it involves like 2 more gates actually. And it was proposed by Professor Kyung-Yeon Cho way back in like 8 years ago, back in like 2014, in order to do French-English translation, basically. So main idea is keep around, you want to keep around memories that could capture long distance dependencies. So you have like your extra memory that keeps your distant input around, and then you allow error messages to flow at different strengths depending on the input. So we'll get to see what this means. So here in standard RNN, this is all you need. If you forget about the bias vector, this is all you need. You have WH and WI, and you just simply linearly transform your previous input and your previous hidden layer and your current input, and then that's it. But in GRU, what you do is you have 2 gates, which is called update gate and a reset gate. You have 2 gates. And what you do is you first calculate your update gate and your reset gate within almost the same manner. You use your current input, previous hidden layer, you linearly transform them, and then you push them through a sigmoid function. This is not tanh, this is sigmoid. This is sigmoid. And this has to be a sigmoid because you want your Z gate values to be between 0 and 1. Same deal with reset gate. You have reset gate, you have H t-1 and xt, you linearly transform, but you see that they are different parameters. This is UZ, this is UR, this is WZ, WR. You have the same sigmoid function, and then you want your R reset gate to have a value between 0 and 1. So Z and R, it's kind of like a gating function. So they work, if it's like 1 is open, if it's 0 is closed. If it's 1 is open, if 0 is closed. So that is why they Professor Kyung-Yeon Cho called it a gate, Z and R. So update gate and reset gate. So you have your gates calculated, and what you do is you calculate your new memory, which is H tilde, which is calculated like this. You have your previous hidden layer, you linearly transform them. You have your current input, you linearly transform them. Instead of simply adding them, you have your RT Hadamard product with your previous hidden layer. So Hadamard product being element-wise product, multiplication basically product. So what your reset gate does is it controls how much your previous memory, previous hidden layer should affect your H tilde. If your R is completely 0, then this term goes away, and your H tilde only consists of your current input, right? But if your reset gate is 1, if it's 1, then your previous input, your previous memory or hidden layer is fully reflected into your H tilde. So that's what RT does here. And then once you have your H tilde, you get your final HT, which is like this. It's a convex combination between your H tilde and your HT-1, which is your previous hidden layer or previous memory with your new memory, H tilde. It's convex combination because it's ZT and 1 minus ZT. So that's where your update gate comes in. If your update gate, ZT equals 0, if it's 0, then what happens here? If it's 0, then this term goes away, and you're only left with your H tilde. So which means that your new memory or new hidden layer is only determined by your H tilde. But if your ZT is 1, then what happens? If ZT is 1, then this term goes away, and your new memory is only determined by, actually it's not even determined, it's copy and paste actually, because it's the same. If it's 1, then HT equals HT minus 1, which means that if your update gate is 1, then your new memory is a copy paste from your previous memory. So that's where ZT, and that's how ZT and RT kind of controls which information flows to the future and which information is prevented from flowing to the future. So that's how GRU can remember for the longer time than RNN, because GRU can, based on these gates, GRU is able to forget unimportant or meaningless information, meaningless input, and then it can keep, or you can retain meaningful or impactful input. So you can control which information is flowed through is propagated to the future, and which information is dropped in the process. So that is why in our vanilla RNN can only handle like maybe 50 to 100 time steps, but GRU or LSTM can handle maybe up to 200 or 300 time steps. So way better than before, and that's why you can handle like, you know, translations and all those complex tasks way better than vanilla RNN. Right, so this is a diagram, but I think we can skip this. So there are a couple more learnable parameters than vanilla RNN, which is in vanilla RNN, we only had U and W, but here we have UZ, WZ, UR, and WR, which are the parameters for different gates. So for update gate and the reset gate. So a bit more learnable parameters, but way better performance. LSTM has one more gate, has input gate, forget gate, and output gate, but the fundamental philosophy is almost the same. It just these gates just controls which information flows to the future and which information does not. So it's just people kind of, you know, use LSTM a bit more often than GRU if I remember correctly, but in my experience, the two just performs exactly the same. You know, it doesn't, like, which performs better. There's just, you know, there's virtually no significant difference. I personally prefer GRU actually, because it has one less gate than LSTM, and it's a bit more, the architecture is a bit more intuitive and more straightforward. But it's up to you which RNN variant you want to use. Right, so that's the LSTM, and then we can move on to sequence to sequence. Actually, we're running out of time, actually. Spend too much time explaining what RNN is. So sequence to sequence is, you use it for exactly this. Given variable length sequence input, you want to predict or generate, you want to output variable length sequence output. So your input is variable length, and your output is also variable length. So in that case, you need to use two RNNs, one for the input, one for the output, right? So what kind of situation calls for this kind of architecture, this variable length input and variable length output, which is like this, like machine translation. You know, you translate from English to French, then you can't predict, there's no guarantee that your input English sentence length and your output French sentence length is exact. There's no guarantee that they two will be the same. So that is why you need to employ sequence to sequence architecture. Same deal with question answering, chatbot, you know, like this. There's a lot of different applications where this sequence to sequence, or in short we call it seek to seek. Seek to seek is used for. Yeah, we need two RNNs. I don't need to. I hope that I don't need to explain why. You know, so. This is a French to English translation. So Je suis étudiant is French for I am a student. So you have an encoder. Which accepts French sentence, and decoder which generates or spits out English corresponding sentence, right? And here you can see that French sentence consists of 4 tokens, including the end of sentence, 4 tokens, and English sentence consists of 5 tokens, including EOS. So That is exactly why you need to use two RNNs, one for the encoder, one for the decoder. So you need to know, you need to remember, you need to know this you need to know, pay attention very carefully that encoders RNN and decoder RNN are completely different RNNs. They're not the same. They don't share any parameters. The W's and U's are completely different. They're completely separate. So you're just training two separate RNNs at the same time. So that was this architecture was proposed by Professor Kyung-Yeon way back in 2014. And this, requiring zero domain knowledge actually, because you don't have to know French or you don't have to know English. You just need to have a parallel corpus where one side is French and one side is English. And then you can just train this model without zero text linguistic domain knowledge or whatever. And that's the power of this sequence to sequence, Back in 2014, there were a lot of language-inspired, heavy domain knowledge-dependent translation models already working pretty well. But what this sequence model does is with zero domain knowledge, without relying on any linguistic domain knowledge, you just pour a bunch of parallel corpus into this RNN, two RNN architectures, and then it just performed decently well. It wasn't the state of the art back in the time, but it performed decently well, and that was kind of like a shock to all the NLP researchers. So that was the historical background. So right, you have one RNN for encoder, one RNN for decoder, and what is the output of encoder? What is the input of decoder? You need to think about this kind of stuff. If inputting Jesu, Etudiant, EOS to the encoder, what do you have as an output? What do you have as an output? Same deal with decoder. If you want to generate or predict each English word at each time step, what kind of input do you need in this here? No. So here, this is the very, very first machine translation architecture, which is that in the encoder side, you have H1, 2, 3, 4. So H4 theoretically representing the entire sentence because it remembers all the words that were given in each time step, right? So H4 becomes your French sentence representation. And what you do is you use this H4 as an input to your decoder. So because decoder S0 has to be initialized to some value, right? Usually S0 was initialized to 0, but here S0 is copy-pasted from H4. H4 is H4. So that is how you pass your French sentence information to the decoder side by copy-pasting your H4 as S0. S0. Then starting with your first word, which we introduced as a start token. So start token, because in order to predict I am a student at each time step, you need to put something inside your decoder RNN. And the first token that you input is something called start token. So you put the start token, which means that start translate now, which means like that. So you put start token, and then you have what do you have? You S1 equals some nonlinear activation function with W start. I'm just gonna write it like this: W start plus U H4 plus B becomes your S1, and you put your S1 into your softmax function in order to predict I here. That's what's happening inside the RNN, in the decoder RNN. And you do this for I. So in order to properly predict, you need to put your actual ground truth input as an input, which is called teacher forcing actually. So you put your I into the next step, and then you force your decoder to predict M. You put M and you teacher RNN to predict A. Same deal with students, same deal with EOS, and that's it. So that's what happens in the decoder side. So the encoder, you put your Jesu Etudiant, and you only take the H4 as your output, and then you use your H4 as the initial hidden layer for your decoder, and then decoder, you simply train it like a language modeling. Like if you remember language modeling, you predict the next word at each time step, right? So that's what happens in the sequence architecture. Right, so the whole thing is trained end to end, because H4 is copy pasted as S0. Copy pasted as 0. So once you have you can do you have 5 loss functions, 5 cross entropy losses, but you can use to backpropagate. So this entire decoder will be decoder's weights will be updated, but at the same time, because H4 is copy pasted as S0, those error signal flows back to the encoder as well. So the encoder's weights are updated too. Right. So that's how you that's how you train your sequence-to-sequence architecture and in an end-to-end manner. Right. So yeah. And in the inference time, in the at test phase, what you do is at test phase, you don't have I am a student as a ground truth input. In the test time, you have to do it all on your own. Your decoder has to generate translate in an autoregressive manner. So what happens is you put Je suis étudiant. So this is fixed, right? Your French input is fixed because it is given to you as an input. So you put your Je suis étudiant end of sentence into your encoder. So you have H4. And what happens then? You copy paste your H4 as your S0, and then you put your start. Well, you know that you have to put your start as an input, right? So that much you know. So using your RNN decoder, you put your start with your S0 as your initial hidden layer. You try to predict at Y1 hat. You predict Y1 hat, and then hopefully it is I, and then you take your I into the next one, and then you try to predict. Then you have your S2 and your I, and then you try to predict Y2, which hopefully is M, and then you do the same thing, the same, until you see your EOS as your output. Then you terminate your translation. So that's how at test phase translations perform. Right. So that's the whole picture of end-to-end machine translation, end-to-end sequence to sequence actually. All right, we only have 15 minutes to go, so I'm not sure if I can cover the entire attention material. Hopefully I can. Any questions so far? All right, I guess there's no question. All right, hopefully I can wrap up attention maybe within 20 minutes. So attention model came along in the same time, almost the same time as the original sequence model, and was also Professor Young Cho was included in the author list, but this was first proposed by Bada now, and the attention was proposed to actually increase the performance of machine translations. Again, so the machine translation researchers are, they have like a huge legacy for us. So are like sequence, attention, transformers, like self-attention, these are all coming from the machine translation research field. And the essence or the core concept of attention is to use all hidden layers from all time steps to make prediction, because as I said, if your sentence becomes longer and longer, then your GRU, even your GRUs cannot exactly remember what happened in the past. I said that GRUs can handle like 200 to 300 time step, but this is like the maximum limit. You don't want to put 200 word sentence into a GRU to perform machine translation. So it's usually like 20 to 50, maybe 50 words or something like that. But even then, GRU kind of like all RNN-based architectures tends to forget what happened in the past. So in order to increase the performance, these researchers, propose something called attention model. So let's use all hidden layers from all time steps to make predictions. So if we're going back to the original sentiment classification example, what you do is we put all tokens or all input, all words into your RNN, and then taking the H10, we put that into logistic regression. So H10 times WO, and then you have a sigmoid function, and then you had your Y hat, right? So that was the core concept of using RNN. for classification. But H10 might or might not remember these early words well. There's no guarantee that H10 would clearly or perfectly remember what happened in the past. So the way that the attention mechanism uses the RNNs to perform classification is this here. So you take all the elements, you take the hidden layers or memories from all time steps, and then you mix them together. So there's a mix. This is called the context vector. You mix them together, and then you use this context vector to do WOC sigmoid, and which is y hat. So how do you mix them? So you don't want to simply average. You don't want to add them all together and then just average them. That would be like a very suboptimal, naive way of mixing. So the researchers actually came up with a very, very nice scheme where you dynamically mix with different weights for each different inputs. So these alphas are the weight, they are the mixing weights. So you have 10 time steps, so you have 10 alphas, and you want your C's to be a weighted sum of your H's, but there's one one constraint, which is that your alpha should sum to 1. So that means that your C is a convex sum of your H's. Like H1 to H10, you want to add them and then add in a manner where you're adding weights, summation weights has to sum to 1. So how do we decide the weight proportion? Like alpha 1 should be 0.1, this should be 0.05, or 0.00002. Like it's not, we can't dictate the weight ratio for each different words. Like it's not like we're always going to use this movie. This is not the only sentence we're going to use. We have infinite number of sentences that could come in, and we can't decide or fix the number. We can decide or dictate the values of alpha every single time. It has to be done automatically by the model. So that's where attention model comes in. Yeah, this is just that we use C to make the final prediction. So what is it good? So as I said, this will be automatically determined. But let's assume that it is automatically determined. What does it go for? Aside from improving performance, you can already assume that this will improve performance, because if you properly mix these H's to a single C, then we're basically using all information from all time steps, and hopefully we will mix important words more heavily than unimportant words. Like this is not a very impactful word, but like Christmas, play, movie, this has more like weights, or this has more meaning to the entire task. So hopefully those will get more alpha weights. So then we can expect increased performance, especially when we are using longer sequences. But besides that, what does it go for? What does it go for? So it's good for actually interpreting which word was more important, because if alphas are properly automatically determined, then we can see which word was more important for making the final prediction. For example, if alpha was like 0.001, but alpha 9 was 0.5, then we can see this is like 500 times more important than this one, right? So we can see that this kind of like gives like an indirect way to interpret what's going on inside the model. So attention is why. That's attention is very, very important for two reasons, like increasing performance and enabling or facilitating interpretation. So the real question is, how do we generate the alpha weights? How does the model automatically determine alpha weights? The answer is we use another function. We use another neural network. In this case, in the original work, they used MLP, two-layer feed-forward neural network, to determine which word should get higher alpha and which word should get a lower alpha. So how does it work? We prepare another separate neural network, feed-forward neural network, which looks like this, which has a very simple architecture. It's just one. In this case, in this example, I'm going to use one single hidden layer. So we have X, one single hidden layer, and output, and that's it. And the output doesn't even have any activation function. It's basically negative infinity to the positive infinity. So it can be, you have your input, and then your output could be any value between. But the important thing is it's a scalar value. It's a scalar value. Your output is a scalar value between the negative infinity and positive infinity. And we're going to call this function y equals ax. So it's an ax4 attention. And what you do is you use your a function to calculate some score for each hidden layer. Like you have h1 to h10, right? Actually, I'm going to have to mute everybody. Right, you have h1 to h10, and then you put your h's into your attention function separately. So you have AH1, AH2, all the way to AH10, and you have corresponding Y1 to Y2 to Y10. And know that this Y1 could be any value between negative infinity and positive infinity, all the way to Y10. And what you do is you get them all together, you get your Y's all together, and then you put them through a softmax function, and that's how you make them into a probability. Because here, this is just 10 different scalar values, but if you put them into a softmax, function, then you get a probability distribution, right? Because softmax normalizes the lotus basically. So you have alpha 1, alpha 2, all the way to alpha 10, which is normalized value from y1 put through a softmax function. So that's how you ensure your softmax ensures that all the alphas sum to 1, right? So if you think about it, it's not that you decide which alpha value should be. It's that this function, a function, decides by looking at h's, it decides which h or which memory or which time step is more important and which memory is less important to decide the final y values, and then you put your y values to a softmax function, and then you get alphas, and then you mix these alphas. Where is it? Yeah. You use those alphas to mix the h's to get the final c value, c vector, the context vector, and then you do a final prediction. So this is all end-to-end. Your NLP, your A function, is also trained at the same time as your RNN, because as you do so you have y hat, so you have y hat, and you have your loss function. So if you do a back propagation, with respect to this loss function, then your WO will be updated, and your W's and U's here will be updated in the RNN. But also you're here, WO here, which actually is different WO, which your WO in your A function and your WH in your A function, these two parameters in your A function will also be updated at the same time. So everything is updated end to end. Your final prediction logit, your final prediction vector, your sigmoid vector, your RNN vectors, your RNN parameters, and your A function parameters all updated at the same time. So that is why it's such a nice architecture, because you don't have to decide your alpha values, because your A function will determine the alpha values properly, and the way the A function is updated, or way the alpha values is determined, is to maximize, or actually no, minimize the loss function. The A function is updated in a way that can minimize the loss function, which is usually cross entropy. So far so good, right? This whole thing is pretty easy, actually. You just employ one more neural network to determine the alpha values for you. You don't decide the alpha value. The NLP function determines the alpha values for you. So this is how you can use attention mechanism when you're doing a sequence level classification. Sequence level classification meaning you put your entire sequence, and then you do one classification at the final time step, which is sentiment classification. But if you want to use attention mechanism in the sequence to sequence manner in the original machine translation paper, how they use attention function is, I'm going to tell you how it's done. So let's assume that we are exactly here. You put your French sentence into your encoder, and you have your H4, and then you copy paste your H4 to be S0, and then you have your start token. You predict your Y1, and then you put your Y1 into next time step, and you put your Y2. You predict your Y2. This is where you are. You need to predict your Y2 given Y1 hat and your start. So this is, and you know that each Y1 is predicted based on S1, Si. So each YI is based on SI. This is pretty obvious because you're in your decoder side, decoder's output is determined by your decoder's hidden layer, which is S. But the problem is that each SI is derived based on what? Derived based on your previous Y, your previous input, previous output, which is your Y. So Y2 is determined by S2, but S2 is determined by what? Determined by S1 and H1, right? I'm sorry, S1 and Y1. So that's what's described here. So you're in this situation. What happens with attention function is that each time you predict your yi, you do an attention mix. You do an attention mixing of your h's every single time you predict your yi's every single time. So this is kind of like a very simple depiction of what's happening here. So instead in the original attention-less sequence-to-sequence architecture, what happens is that H4 is determined, and you use your H4 all the time. You put your French sentence, and you derive your H4, and H4 is fixed as an S0, and then you go along with it. H4 is reused every single time you predict your Y1, Y2, Y3, Y4, Y5, all the way to the EOS, right? That was your original attention-less architecture. In the attention architecture, what happens is that you don't use H4 anymore. You dynamically mix your H's to make a context vector, and then you make your context vector every single time you predict your Y1, Y2, Y3, Y4. When you're predicting Y1, you use C1. When you're predicting Y2, you dynamically create C2, context vector 2. When you're predicting Y3, you create context vector 3, C3, Y4, C4, Y5, C5, something like that. So that's how it works in the attention mechanism for sequence to sequence. So here, your yi still is determined by si, which is pretty obvious. But your si is no longer derived from only two things. It is actually derived by three things: your previous s, which is previously layer, your previous output, obviously, and the context vector ci. So what is a context vector ci? Context vector ci is a dynamic mix of h's. So SCI is derived from SI minus 1 H1 to T. So SI minus 1 to H1 to T, which means that your CI, so there's another function called MLP. Let's call this function MLP, attention function. And this gives you a CI. And this receives SI minus 1 and H1, H2, H3, H4. You put this H, all the H's, and your previous hidden layer in the decoder time step, and then you decide CI. So that's what your attention function does. So dynamically. So when you're predicting Y2, you need S2, but S2 is determined by S1, C2, and Y1. And C2 is determined by what? C2 is determined by S1 and H1, 2, 3, 4. You do this, and then you repeat this for Y3 as well. You go to Y3 hat, S3, and you have here C3 and Y2 hat. So every single time step, you dynamically mix or pull your H's according to the compatibility between SI minus 1 and H1, SI minus 1, and so basically there is always a pairwise comparison. How compatible are they? How compatible are they? And how compatible are they? And how compatible are they? Like this. And then depending on the compatibility score, your Y scores, the normalized score will be determined. And then you put it through a softmax function to determine alpha scores. And then you use those alpha scores to mix them together to get C. Hopefully that makes sense. Right. So yeah, this is a bit more detailed mathematical formula of how you can do it. So as I said, you always calculate the compatibility between SI minus 1 and H1, S minus 1, H2, all the way to SI minus HT. Based on this score, you put it through a softmax, and then you get your alphas, and then you get your summation. Once you have the alphas, you can derive your context vector, and then based on the context vector, you can do this. You can take all these three you can take S1, C2, Y1 to derive S2, and then you get your you can predict your Y2. Right. So if you think about it, it's pretty straightforward. If you understand the concept of attention function properly, then you can see where you can use it. whether it's a language modeling, whether it's a sentence sequence level classification, whether it's a sentence, so whether it's sentiment classification, whether it's language modeling, whether it's translation, anywhere, as long as you want to mix your H's properly, you can use attention function as a separate component, like an additional component to decide the alpha values for you, which will be trained end to end. So last, very last depiction of how you can use attention to kind of interpret what's going on is this. So what you want to do is you want to, I think this is English, yeah, English to French translation. I borrowed this figure from the original paper. So they are trying to translate English sentence to a French sentence. So English sentence being this: destruction of the equipment means that Syria can no longer produce new chemical weapons. So you have you put your English sentence into the encoder, and then you want to decode, you want to generate a corresponding French sentence. And since we're using attention mechanism, each time we predict a French word at each time step, you are dynamically mixing your English words or English hidden layers, actually, hidden layers of the English sentence. And you can see that, for example, when you're predicting the word destruction, or the French word destruction, you dynamically mix the English hidden layers, and the highlighted one is the one that received the maximum alpha value. So this is alpha 1, this is alpha 1, alpha 2, alpha 3, alpha 4, all the way to like alpha 15, whatever. And it means that when predicting the French word destruction, it happened that alpha 1 received the highest value. And it kind of makes sense because the English word destruction should be used to predict the French word destruction, right? Same deal here, equipment. Well, this is not, this is probably pronounced differently, but French word equipment, when the decoder is predicting the French word equipment, convex combination is happening here with proper alpha values. And it happened that alpha 4 received the highest value, highest softmax value. And makes sense, it's natural, because English word equipment should be used to predict the French equipment, right? Same deal. And the same with la Syrie, both la and Syria. So la Syrie should be like, probably is Syria, right? So la Syrie, both times, Syria was maximally used both times to predict both words. So by studying the attentional waves, you can kind of see what's happening inside the RNN or inside the neural network model. And because these two languages, French and English, these two languages come from the same Latin root, they have a very similar linguistic structure. So that is why you see a very nice looking diagonal line here. If it was like English to Korean translation, then this wouldn't be as like diagonal as it's here, because their word linguistic structures and syntactic structures are very different. Anyway, so yeah, so attention not only increases the performance of your model, but also gives you a peek at the inner workings of the model. And there were kind of a debate as to if you can treat attention as a proper interpretation or not. So there was like a paper called "Attention is not interpretation." Oh, sorry, attention is not explanation. And then the follow-up paper, "Attention is not explanation." So there was kind of a debate going on back in like 2020 or 2019. Still, it's a nice figure though. So, all right. So this is the end of the class today. So sorry for running a bit later than usual. So we are running 10 minutes overboard. If you have any question, do you have any questions so far? Like, I'm gonna wait maybe 5 seconds before I end the class. If you do have questions, you can ask now, or if you don't have questions but think of a question later, you can always use Classroom. So RNN might not be as important as before, like, because we are now living in the world world of transformer these days. But the concept of attention is super important, because transformer is just attention all the way. It's called self-attention. So transform is nothing but just a self-attention, stacked self-attention. So understanding the concept of attention is really important for the future material. All right, so if there's a question, let's end the class today. And coming Thursday, you guys will be implementing RNNs and then trying to play around with RNN and GRUs. All right, I'll see you guys next week, and thank you very much. Bye-bye. Oh, sorry, there was a question. Sorry. Is there a loss function for the attention model? No, as I said, attention은 아까 얘기했듯이 very good question. 아주 좋은 question인데 attention 아까 얘기했듯이 어텐션에 이제 요거랑 W랑 WH를 이제 업데이트를 해야 되잖아요. 근데 그게 아까 보여드렸던 요거 여기 마지막에 이제 Y 햇이 나오고 그다음에 이거 가지고 로스 펑션이 나오는데 이거를 백 프로파게이트 하면은 자동으로 다 흘러 들어가게 됩니다. 그 에러 시그널이 지금 여기에 W5도 업데이트를 할 수 있고 여기 RNN에 있는 이제 W랑 U도 업데이트 할 수 있겠지만 당연히 근데 지금 보면 이 C를 거쳐 가야 되잖아요. 지금 이 에러 시그널이 쭉 오면서 다 지우면은 에러 시그널이 백 프로파게이트 하면서 여기 한번 거쳐가고 이렇게 쫙 오고 쫙 해서 여기서 다시 W 아니죠. 여긴 W가 아니지. 그러니까 이제 WH WX, WH 이런 식으로 WH, WX 이렇게 있는데 쫙쫙쫙 흘러가면서 요거 업데이트되고 요거 업데이트되고 요거 다 업데이트될 텐데 그 와중에 C를 거쳐가잖아요. 근데 C를 거쳐간다는 건 C를 만들기 위해서 아까 MLP가 사용이 되잖아요. 아까 MLP가 얘가 사용이 되거든요. C를 만들기 위해서. 그러니까 C를 만들기 위해서 얘가 사용되면서 그 안에 W랑 WH가 또 있기 때문에 걔가 자동으로 업데이트가 됩니다. 흘러가면서. 에러 시그널이 흘러가면서. 그러니까 별개의 로스 펑션이 필요가 없어요. 그냥 이 모델 전체가 하나의 워킹 모델이고 그거는 오로지 뭐 트랜슬레이션이든 뭐 센티미터 클래시피케이션 뭘 하기 위한 로스 펑션이 있을 테고 그 로스 펑션으로 엔드 투 엔드로 학습이 다 됩니다. 이해가 되셨을까요? 네, 좋습니다. All right, thank you for the question, and I'll see you guys next week. Bye bye. 네, 감사합니다. 감사합니다.